Hi boys and girls, this is lecture 3.9, the last lecture in Unit 3. The topic, Rolle's theorem and the mean value theorem. We're going to conclude the Unit 3 lectures with a discussion of two more continuity theorems, Rolle's theorem and the mean value theorem, and we'll start with Rolle's theorem. It states, let f, the function, be continuous on the closed interval ab and differentiable in the open interval ab. If f of a equals f of b, then there is at least one number c in the interval ab such that f prime of c equals 0. Now what is this saying? Let's look at this picture and illustrate it here. If our function is continuous and differentiable on this interval, those conditions being met, we then say if f of a, the function value at a, the left endpoint of the interval, equals f of b, the function value at b, the right endpoint of the interval. If those function values are equal, then there's at least one number c in the interval ab such that f prime of c equals 0. There has to be a place then where the slope was 0. Let's think about it this way. If the endpoints of the interval are the same value and we have a continuous function here, then this is what has to happen. Starting at this point and knowing that I have to come back down to the same value by the time I get to this endpoint means that a smooth and differentiable function is going to go through a max or possibly a min value to get back to where it started. There's no way to go up without coming back down. And in the process of coming back down, having that brief moment where the slope was 0 and indicating a maximum value, or there's no way to come down without coming back up, again with that one brief moment where the slope was 0. Now understand this theorem guarantees us at least one such value, but depending on the complexity of the function, there could be more than one. We're just guaranteed at least one. What if the function did something like this? As long as it started at one place and came back to the same place, we know that it had to go through a slope of 0 at least once. In what I've drawn here, we see 1, 2, 3 times that happened, but at least one time it's definitely going to happen, as I said, starting at one point and coming back down to that same point or coming back up to that same point. We had to have a place where there was a slope of 0, a max or a min. Now look at this scenario. Here is where we have a continuous function but not differentiable. We might think that Rolle's theorem should apply here. After all, we had to start here at this function value and we ended up here. Doesn't it make sense that if this was continuous, that we would definitely have gone through a place where the slope was 0? Well, not if the function wasn't differentiable. Notice in this case, we moved up, we came to a place where the function was defined and continuous, but not differentiable, came back down. You can see that there's no place on this curve where the slope is 0. So Rolle's theorem is only guaranteed when the function is continuous and differentiable. We need the function to be smoothly moving through all of the slopes to come back down to the same value so that it will go through a slope of 0. So now let's look at a couple of examples where we put Rolle's theorem into practice. Here's the first one. Find two x-intercepts of f of x equals x squared minus 3x plus 2 and show that f prime of x equals 0 at some point between the two x-intercepts. Now what's going to happen is when we find our x-intercepts, there are two of them, we'll say that they are a and b. Those will be the endpoints of the interval that we're looking at. Because they are intercepts and they'll both have a function value of 0, this will mean that it will meet the condition that f of a equals f of b. Then we're going to look for a value between a and b at where the slope of the function is equal to 0. But first we need to find the x-intercepts. So let's take our original function and set it equal to 0. I know we can see them from the graph, but we don't always have the graph, and many times we'll be doing this without the graph available or without our graphing calculator available, so we need to get used to the analysis. Fortunately, this factors easily into x minus 2, x minus 1, giving us zeros or solutions at 1 and at 2. So the point is that we're going to look for something between 1 and 2, a place where the slope of the tangent line to the curve will be 0. The condition that f of a equals f of b works here because since these are zeros and f of 1 is equal to 0, f of 2 equals 0, well then of course f of a equals f of b. We also know that the function is continuous and differentiable here because it's a polynomial. For polynomials, the function is continuous and differentiable on its entire domain. Therefore, it's definitely continuous and differentiable between 1 and 2. All right, now let's try to find the value between 1 and 2 where the slope is 0. We're guaranteed that there is at least one place. Even if we didn't see it, we would know it was there. We'll need to take the first derivative to find it. F prime of x is equal to 2x minus 3. And so we're wondering, where is there a slope of 0? Set the derivative function equal to 0 to find that value. It turns out that at 3/2 the function has a slope of 0. Notice 3/2 is between 1 and 2, so Rolle's theorem guaranteed us a value which we then found by taking the first derivative and setting it equal to 0. All right, here is another example where Rolle's theorem will be illustrated. Let f of x equal x to the 4th minus 2x squared. Find all values of c in the interval -2, 2 such that f prime of c is equal to 0. All right, we need to see if Rolle's theorem is going to apply on this interval before we start looking for whether or not something is guaranteed in the interval. So remember, first of all, we need a differentiable and continuous function. Since we have a polynomial, no worries there. The function will definitely be differentiable and continuous on the interval -2, 2. Well, then the other condition that needs to be met is, does f of a equal f of b? A and B represent the endpoints of the interval. So what we're wondering is, does f of -2 equal f of +2? So let's find the value of f of -2. This is going to be positive 16 minus 8, which is 8, and f of +2 is 16 minus 8 again, which gives us 8. So this condition is met, and the function is continuous and differentiable. Therefore, we are guaranteed at least one value between -2 and 2 where the slope of the tangent line to the curve is 0. As you can see from the graph, it looks like there are more than one such place, but we are going to use our analysis to find out what they are. So we're going to take the derivative of the function. F prime of x is equal to 4x cubed minus 4x. Let's set this equal to 0 and factor out 4x. This gives us x squared minus 1, which can be factored further. 4x and then x minus 1, x plus 1. Each of these three factors, set equal to 0, will generate a value for us, a place where the slope is 0. This one is going to be at 0, and then x minus 1 equals 0 gives us x equals 1, and then x plus 1 equals 0 gives us x equals -1. So we didn't just find one place between -2 and 2 where the slope is 0, we found three places, at -1, at 0, and at +1. All right, now it's time for our second theorem, the mean value theorem. If f is continuous on the closed interval AB and differentiable in the open interval AB, then there exists a number c in the interval AB such that f prime of c equals f of b minus f of a over b minus a. So it's a little bit different than Rolle's theorem. Here's what this is saying. F of b minus f of a over b minus a is the slope of the line connecting the endpoints of the interval. If we're saying that our interval is AB and we drew a line connecting f of A to f of B, this secant line has a slope that we could find by subtracting the y values, f of B minus f of A, over the subtracting of the x values, b minus a. So this is the slope of the secant line. What the mean value theorem is saying is that if the function is continuous and differentiable between f of A and f of B, there exists at least one place in that interval where we will have a tangent line to the graph that has the same slope as the secant line connecting f of A and f of B. So what you're going to do first is determine whether or not it's a continuous and differentiable function in that interval. Secondly, you're going to find the slope of the line connecting the endpoints by just using the slope formula. Then you're going to take the derivative and set it equal to the slope that you find, because the mean value theorem guarantees you at least one place in this interval where the slope will be equal to the slope of the secant line. As I have said before, there could be more than one place. Let's say your function looked like this instead of what I have here. Then it looks like maybe there's a spot right here that has the same slope as the secant line, maybe right here, and perhaps another one about right here. You get the idea, but we're guaranteed at least one. Now I want to mention that Rolle's theorem is a special case of the mean value theorem. Think about what we're asking to happen in Rolle's theorem. We want f of A to equal f of B. Well, if those function values were the same, the secant line connecting them would have a slope of 0. And then, of course, in Rolle's theorem, we're asked to find a c within that interval where the derivative is 0. So Rolle's theorem is really a special case of the mean value theorem where the slope of the secant line is 0. But in the mean value theorem in general, whatever the slope of the secant line is, we're saying that there's at least one place between A and B where we'll find the slope of a tangent line to the curve with that same slope as the secant line. All right, let's give this a try. Given f of x equals 5 minus 4 over x, find all values of c in the open interval 1, 4, such that f prime of c equals f of b minus f of a over b minus a. Well, first we need to know if the function is differentiable and continuous between our two endpoints. At first we may wonder, because as you can see in this function, there is definitely a place where it's not defined, therefore it won't be continuous. That is at x equals 0, but fortunately that's not in the interval that we are talking about. So for the interval 1, 4, the function is continuous and differentiable. Now let's find the slope of the secant line connecting the two endpoints. The ordered pairs there are 1, 1 and 4, 4. The slope therefore will be 4 minus 1 over 4 minus 1, 3 over 3, which is 1. So we're looking for places in this interval where the slope of a tangent line to the curve is 1, and we're guaranteed at least one place. Now it's time to take the derivative. F of x equals 5 minus, I'll write this as 4x to the negative 1. Therefore, f prime of x is going to be positive 4x to the negative 2, which is 4 over x squared. Remember, we're not setting this equal to 0. We want our slope function to tell us where there is a point that has a slope of 1. When we cross multiply here, we get x squared equals 4, which generates two places on this curve where there is a slope of 1, but only positive 2 is in the interval 1, 4. What is the y value when the x is 2? Plugging that back into the original function gives us a y value of 3. So at the point 2, 3, which is about right here, the slope of the tangent line at that point is the same as the slope of the secant line that connects the two endpoints. Let's write the equation of that line. Y minus 3 equals 1, our slope, times x minus 2. And this gives us an equation of y equals x plus 1. And here is that tangent line. That's it for today's lecture, and that concludes the Unit 3 lectures. Speaking of roles, classic, elegant, timeless. God bless you, boys and girls.